All right, peace, love, science. Science! Huh. Funky, funky science. Oh, funky, funky, funky science, yeah. Oh, funky, funky, funky science, yeah. The second episode of Funky Science Story Hour, and I'm so happy to see you here. I can't really see you, but you can see me. Well, you can't really see me either. You can see a screen that has something like me on it, a two-dimensional representation of a three-dimensional me here on your screen, and I'm happy about that. And the idea for this next hour is that we're going to have a little bit of fun with some funky science. Hey there, Patrick. Yeah, I know, Dr. Boomer. Dr. Boomer doesn't know how the thing works. Gotta figure it out. All right, well, Dr. Boomer, Dr. Funky Spoon is here. And of course, we're going to start off with a Funky Science Story Hour theme song, because that's how we start off. All right? Gather round, my children, pull up a chair, my friends. Let's all get together for the story that never ends. How did we get here? What's inside your head? What's bluer than blue? What's redder than red? Gather around, my people, all children, young and old. Pull up a seat, put up your feet for the greatest story ever told. Funky Science Story Hour, 'cause knowledge is science and knowledge is power. Whoops, I screwed that up. I'm gonna do that part again. Through the magic of science. Funky Science Story Hour, 'cause science is knowledge and knowledge is power. Because the world's so weird and weirdness is fun, 'cause we've so much to learn and we've all just begun. Oh, we can learn together, we can understand the weather, we can imagine ourselves in any place. We can see the earth, we can see the earth from outer space. How do we do that? Well, with science. Funky science. Science, science, science. Funky, funky science. Funky, funky, funky science, yeah. With science. Funky, funky science. Science, science, science. Funky, funky science. Science, science. Funky, funky science. Oh, we can learn together. We can understand the weather. We can imagine ourselves in any place. We can see the earth from outer space. Yeah, Funky Science Story Hour, 'cause science is knowledge and knowledge is power. Because the world is so weird and weirdness is fun, and there's so much to learn and we've all just begun. Man, I got a lot to learn. Oh, with science. Funky, funky science. Yeah, science, science, science. Funky, funky science. Oh, science, science. Funky, funky science. One more time, everybody sing along. With science. You can dance if you want to. Funky, funky science. Oh, science, science. Funky, funky science. Yeah, funky, Yes, yeah. Thank you. Maria says we need a choreography for this song. Yes, we do. Hi, Bart. I think we do, and that's going to be the Funky Science Challenge for next week. Whoever sends me a video with the best choreography for the Funky Science theme song wins, I don't know, a signed book and a private astrobiology lesson or something. You'll win something good if you come up with a choreography for the Funky Science theme song. Hey, Shaddy. So cool to see you all streaming across my screen here. I'm going to pull up here the comments on another little window here so I can make sure and keep track of the festivities. Oh, that's so funny. I've got Bluetooth going and I'm blasting it the upstairs speakers. Whoops, my poor wife. I'm going to turn that off now. Sorry, Jennifer. I think she was on a work phone call. Man, you know, technology. Technology. We love it and it frustrates us at the same time. Tools. Humans are tool makers. And we make these tools that even we don't understand how to use. That's why we need the aliens to come down here to Earth right now. Right now, aliens, come down and tell us how to use our tools. Because we're too clever for our own good and we invent things that we don't know how to use. You know, like industrial civilizations and things like that. It's aliens. I told you there were going to be aliens on this show. All right. But seriously, this is serious. Science is serious. This is, get rid of that. All right. We're going to do some science now. Everybody stop smiling. Get serious. Sorry. I'm not very good at that part. Okay. I had some questions that you all sent in last time or in the interim time between last time and this time. That's called a week, in the week in between. And I'm going to get to some of those questions now. And then also feel free to send me more questions as this hour goes by. Only it's hard to sometimes catch things as they're streaming. But if you want to shout out, give me your name and your age. We had, so Sabin, here's one that we got. Sabin, age 6. Hey, Sabin, I hope you're watching. Nice to see you. Sabin, age 6, would like to know what it's like on Venus. Oh, man. So would I. Sabin, you and I, we think similarly, because I would like to know what it's like on Venus. But I'll tell you what I know. I know a little bit about what it's like on Venus, although I want to know more, because that's why we need to send more spacecraft there to find out. He'd also like to know if you think time travel is possible. If you think time travel is possible.
Time travel is possible.
If you think time travel is possible. Travel is possible. He spent yesterday time traveling in a laundry basket. Oh. He spent yesterday time traveling in a laundry basket. Oh, man.
He spent yesterday time traveling in a laundry basket. Oh, man. He spent yesterday time traveling in a laundry basket. Oh, man.
Oh, man, Sabin. You sound like a cool kid.
Oh, man, Sabin. You sound like a cool kid. All right. So what's it like on Venus? We do know some things about Venus. Venus is an intense place. I mean, one thing to realize about Venus, first of all, it's the closest planet to Earth. I mean, where it is at any given time depends on the orbits, because Earth is orbiting the sun and Venus is orbiting the sun a little bit closer than Earth, about 3/4 of the distance. So if this is the sun and this is Earth, Venus's orbit is about that far. Earth, Venus from the sun. So they're both orbiting around all the time, and Venus orbits faster than Earth because planets on the inside lane always orbit faster than the planets on the outside lane because gravity's pulling them faster, okay? So Venus is always passing us in Earth's orbit, but when it comes close, it's about the closest planet There is. It comes about, something like 30 million miles away. That doesn't sound that close, but it's pretty close. The sun is 93 million miles away. Okay? So, and Venus, by the way, is also, because it's the closest planet and because it's big, I mean, big for a rocky planet, it's the same size as Earth. Venus, sometimes we call it Earth's twin planet because it's basically the same size. And Venus is very bright in the sky. And the reason it's so bright is because it's completely covered with clouds all the time. It's like you look up on Earth and sometimes it's a clear blue sky, sometimes it's cloudy. If you were on Venus and you looked up, it would be cloudy all the time everywhere. And as a result, the light from the sun bounces off those clouds. It's very bright. It's like a bright reflector. You know those, think of something that's really bright and reflects. I mean, well, this white paper is pretty bright, but think of something even brighter than that. Like those things you wear at night when you're bicycle riding to not get hit by a car so you'll be really reflective. Venus is the most reflective planet there is. It's really bright. It bounces all the light back almost from the sun because of those bright clouds. And the reason I'm going on about this is to tell you something cool, which is that right now, Venus is very, very easy to spot in the sky. So tonight, this evening, you should all go out in your yard, keeping a safe social distance, making sure that your parents know where you are, and they should go with you too. But you should go outside when it's starting to get dark and look up to the west, the same direction that the sun sets, the west. And you'll see a very bright, it looks like a star, but it's brighter than any star. And there's Venus in our evening sky right now. Not right now, well, depending on where you are on Earth, it might be right now. But tonight and tomorrow night, Venus sometimes is an evening, we call it an evening star, sometimes it's a morning star because before it passes Earth, it's in the evening, and then after it passes Earth, it's in the morning. So right now, you can see Venus. So what's it like on Venus if you go below those clouds? And we've had some spacecraft that have gone below those clouds and taken measurements, measured the temperature and measured the gases to see what they're made out of, and done other experiments. So we know some things. And the most amazing thing about Venus is that it's very, very hot there. Much hotter than the hottest place on Earth. How hot? Well, in terms of Fahrenheit, which we Americans seem to use a lot, it's about 900 degrees Fahrenheit on the surface. That's just so hot. That's like if you take your oven, don't try this at home, folks, but if you turn it all the way up, even more than all the way up, if you put it, some ovens have a self-cleaning function where they get hotter than the hottest setting so that they can burn off whatever and clean themselves. That's how hot Venus is. The hottest ovens the hottest setting on your oven. It's 900 degrees all the time. Why is it so hot on Venus? Well, I'll tell you one clue. Well, for one thing, as I mentioned, it's closer to the sun than Earth, so there's more radiation from the sun. But I also mentioned that most of that radiation is bouncing off the clouds, so actually not much of that sun's radiation is reaching the surface. So why is it so hot? It's because Venus has a really intense greenhouse effect. Have you guys heard about the greenhouse effect? It's what makes Earth hotter than it would be if there are some gases in the atmosphere. I mean, in Earth's atmosphere, there's all this oxygen we can breathe, and there's something called nitrogen. But there's also a little bit of something you may have heard of in Earth's atmosphere called carbon dioxide. And carbon dioxide makes planets hotter because it absorbs, it blocks the heat. The light comes down from the sun, and it warms up the planet, and then that heat wants to escape. But if there's some gases in the atmosphere that block that heat from escaping to space, the planet heats up, and one of those gases is carbon dioxide. There's a little bit of that carbon dioxide on Earth, and you may have heard some of us are kind of worried about the fact that we're we're increasing carbon dioxide on Earth with our exhaust from our cars and other things we're doing, and that's that we're changing, we're heating up the Earth. We call that climate change, and we're kind of worried about that. We have to figure out how to stop doing that, before we harm our planet. So, but it's really interesting. If you look at Venus, the atmosphere there is all carbon dioxide. Here on Earth, a little bit of carbon dioxide is heating up our planet. If you go to our sister planet, Venus, the atmosphere is basically, well, it's more than 96%. So there's little bits of other stuff, but it's basically all carbon dioxide. And so that blocks all the radiation that's trying to escape into space, all the heat, and it keeps Venus very, very hot. So what's it like on Venus? It's hot, and if you were standing on Venus, well, first of all, I hope if you're standing on Venus, you have a very good spacesuit, because otherwise you wouldn't survive very long because of that heat. The other thing is that what we call the atmospheric pressure is really huge on Venus. What do I mean by the atmospheric pressure? It's just the force of all the air. You don't feel it because you're in the air, but the air is pushing on everything from every direction, and that's why when you go up to the top of a mountain, it's a little bit harder to breathe. You can get out of breath at the top of a mountain because there's a little bit less air pressure. And if you go up in an airplane, they have to keep the cabin pressurized because there's even less air pressure. Well, on Venus, it's much higher pressure than even at the surface of the Earth. It's about 100 times the air pressure. So there's a lot of air, and it's very dense, and it's very hot. But the other weird thing is, because of those clouds everywhere, you would never see the sun on the surface of Venus. You wouldn't have any shadows. You would be able to see because there's enough light just filtering through the clouds, just like you can see on Earth on a very cloudy day, but you don't have shadows, right? That's what it's like on Venus. It's like a very cloudy day all the time, and it's very hot. The gravity on Venus is about the same as the gravity on Earth because Venus is the same size as Earth. So if you were walking around on Venus, it would feel like you were walking on Earth. It wouldn't be like the moon where you're like, bleh, or Mars where, you know, if you're walking on Venus, it'd be pretty much like, oh yeah, I got this. This is like walking on Earth. But you would need a really good suit because of the pressure and the temperature. And also the light on Venus is kind of reddish. Everything would look sort of red. And that's because, do you remember last time we talked about why the sky is blue on Earth? And it's because of the scattering of the light. And the blue light gets scattered easier. And that's why sunsets on Earth look red. Do you remember that? That was from, you can go back and review your lesson from last time. Look at the tape last time we talked about why the sky is blue. So on Venus, that makes the light red because the air is so thick, the atmosphere is so thick, that the light that finally filters down and makes it through to the surface, most of the blue light has been scattered away, and it's mostly more red light that reaches the surface. So it would be hot, it would be dry, everything would look red. And then in terms of the rocks, it depends on where you are on Venus, what you would actually see around you, because just like Earth, Venus is a complex planet. Like if you say you were talking to somebody from another planet and they said, what's it like on Earth? You'd tell them some things, but then you would say, well, it depends where you are. Because what if you landed in the desert? It would be different from if you landed in the ocean, or if you landed on the top of a mountain, or if you landed in a parking lot at Safeway. So different places on Earth are different. And the same thing with Venus. We don't think there are any Safeways there. There are no oceans there, but there are mountains, there are volcanoes, there are valleys, there are canyons, there are sand dunes, there are some craters, which are big holes in the ground that cause when asteroids hit Venus from space. So there's a lot of different places kinds of places on Venus depending on where you land. A lot of Venus is covered up with volcanic flows. So if you landed on some average place on Venus, chances are you'd be on some kind of a volcanic formation, maybe a smooth surface of old, what we call basalt, which is like dark volcanic rock. But it really would depend on where you are. So that's kind of what we can say about what it's like on Venus. There's a lot that we still don't know, and that's why me and some of my friends are trying to, we want to send more spacecraft to Venus so that we can learn more. And maybe when some of you grow up, if you're interested in that, you can maybe even get a job helping to explore the universe. And if you are interested in doing what I do, you could study planetary science and you could help us explore Venus and other planets. We need help, and there's a lot more to explore. We've just begun. There's so much that we don't know. I can tell you some things we know, but there's so much more that we don't know, and that's what's cool about science and exploration, is that there's so much to find out. Okay, great question, Sabin. Oh, Sabin also wanted to know if I think time travel is possible. Yes, time travel is possible. I can prove it, Sabin. Okay, here's how I'll prove it. Where I am now, it's 3:33. And I am going to now attempt to travel in time. Attempt to travel in time. In time. It's an experiment. Are you with me? Are you guys watching? We're going to travel in time now. It's 3:33. Now, I am going to travel forward in time by 1 minute. All right? See if you can do it with me. Let's all hold hands, not for real because we're social distancing, but over the internet. We're holding hands and we're going concentrating, and we're going to see if we can travel forward in time 1 minute. Okay, it's 3:33. Let's see if we can do it. Everybody focus. Time travel forward in time. Can we do it? Are you trying? Somebody's not concentrating. It's not working. Come on. Everybody concentrate. Forward in time, 1 minute, 1 minute. It worked! It's 3:34. We did it. We time traveled. Woohoo! So, Sabin, the answer is yes. Time travel is possible. We just did it. Now, what you might be thinking is, oh, cool. Hi, Melanie. Hi, Sabin. I'm so glad you guys are watching because you asked such good questions, Sabin. And Sabin's only 6. Imagine what kinds of questions he's going to have when he travels in time into the future, and he's 7. Oh my God, kids just gonna blow our minds. All right. So, but the thing is, you may want to know: can we travel in time other ways than that? Like, could we go back in time, build a machine where we could go back in time 100 years and explore, or go in to see what the future's like? And my first answer is no, we can't do that. But my second answer is, well, who am I to say we can't do that? There's nothing we know about the universe that tells us we could travel in time. There are some things we know about the universe that suggest that if we could travel in time, it would be pretty weird, right? It would lead to, we call these time travel paradoxes. Like, what if I went back in time and what if I went back in time 65 years and I convinced my parents that they should not have children? I talked to them and said, you know what? Maybe it's just you'd enjoy your life more if you had the freedom to do what you want and didn't have to, pay for college and stuff. Maybe you shouldn't have children. So what if I went back in time and convinced my parents that, and they were like, you're right. And they decided not to. Well, then what happens to the me that traveled back in time? Do I just go poof and cease to exist? But if I went poof and cease to exist, then nobody would have gone back in time and convinced my parents that they should not have children. In which case, they would have, and then I'd go poof, and I'd be back again. So, either way, it doesn't make sense. It's a paradox. So, I think probably time travel is not possible, but we're so ignorant about the universe. But here's one other way in which time travel might be sort of possible. There's one thing we've learned about the universe that's really weird, and some of the things we learn about the universe using science are just weird. You go like, wait, really? Is that true? And how could that be true? And then you do experiments and you go, wow, that really is true. And one of those things is, you may have heard of Einstein's theory of relativity. Have you ever heard about that? Einstein, you've seen pictures of Einstein. He's that guy with the mustache and the hair like I used to have. And he was this really smart guy, this brilliant person who figured out a lot of things about our universe that seemed too weird to be true, and then it turns out they are true. And one of those is what we call the special theory of relativity. And I'm not going to explain the entire special theory of relativity to you, although I know that Sabin could handle it because he's such a smart kid. But one thing we learned from that theory is that if you go really fast, like much faster than any machine on Earth goes, but if you sent a rocket in space that went really, really fast, so that it was going almost the speed of light. The speed of light is the fastest speed in the universe. It's the speed with which, I talked about this last time, but I turn on a light and there are what we call photons of light coming out of that bulb and bouncing around the room and bouncing into our eyes so we can see. And that is not infinitely fast. There's actually a speed. It takes a little bit of time for light to go from here to here. And it's so fast that it seems like it takes no time. But if you're in space and the distances are large enough, then you realize light does have a speed. That's why it takes a couple seconds to hear the astronauts when Houston talks to the Apollo astronauts. It's why it takes hours for us to send a signal to the New Horizons spacecraft when it's out at Pluto, because at that distance, the speed of light takes time. So the speed of light is the fastest anything can go in the universe. But it turns out that when something else, a rocket or something in space, goes close to the speed of light, then something really weird happens. Time slows down. If you accelerate something, if you move something so fast that it's almost the speed of light, then time slows down. So that if you were a person and you got on a rocket ship and that rocket ship accelerated and fired its rocket and accelerated and fired its rocket and went faster and faster and faster and faster so that it was going almost the speed of light, and then it went all the way to, say, another star system, like the nearest stars are about 4 light years away, which means it takes 4 years at the speed of light to get to those stars. So say you went to the nearest stars and then, or even farther, to a star that was hundreds or thousands of light years away, moving really fast at the speed of light. And then if you came back to Earth, because time had slowed down on your rocket moving so fast compared to Earth, then much more time would have passed on Earth than would have passed in your rocket. So you would show up on Earth and the people that you knew when you left Earth might not be alive anymore. It might be a completely different generation on Earth. So it would be as if you had traveled in time. So there are ways that we can imagine doing something that's like time travel by traveling. We call that traveling at relativistic speeds in space. So that's kind of a weird example. But I would say basically, as far as we know, you can't time travel, Sabin. But I would also say you have to add, as far as we know. That phrase is important to add in science for a lot of things because there's so little we know. You might think that scientists know so much and they've got all this stuff to teach you, and that's true. We do know, there's certain things that we've figured out about the universe that are really cool and you have to study for years to understand. But it's also true that given how much we don't know, that we're just scratching the surface. And so when you ask a question like that, I have to say, well, here's what scientists might think now, but we can't be completely sure. Oh, and you did spend yesterday time traveling in a laundry basket, Sabin, so I would be interested sometime in knowing how that worked. Okay, another question. Phineas, age 12. Hi, Phineas. Is interested in both paleontology and space. And he wants to know, is there Astro Paleontology? That is such a great question. I love that question. Is there Astro Paleontology? Yes, of course. Just like there's astrobiology. With astrobiology, which is what I do, we study the question of alien life. Now, this guy notwithstanding, we don't actually know if there is alien life. We think there is life elsewhere in the universe, but how do we study that? What does an astrobiologist do? Like me, why am I not out of work like everyone else right now? Because we don't know of any aliens. What we study is we study life on Earth, its history, its limits, what its nature is, where it can survive. And we study the conditions on other planets. What is it like on Mars? What was it like on Mars in the past? What is it like on the moons of Jupiter? Where are there places, environments in the solar system or even beyond the solar system where, given what we know about life on Earth, where there might be life? And so astrobiologists study the question of life elsewhere, even though we haven't found life elsewhere. And so you're asking about astropaleontology. And yes, what do paleontologists do? They study fossils. They dig up fossils. They think about what those fossils tell us about life in the past and about how life evolves. Well, there are certainly people looking for fossils on Mars and people wondering about how the signs of life would survive over billions of years on different planets. And it may be that when astrobiologists find signs of life elsewhere, hey John, hey Kat, it may be that when astrobiologists find signs of life elsewhere, that we won't find living things, we'll find fossils, or we'll find signs that life was once there. And who would we need to help us understand that? An astropaleontologist. So, Phineas, in answer to your question, yes, astropaleontology is a great idea for a field. There are people that are interested in that within astrobiology. And so if you're interested in both paleontology and space, I think there's a future for you in astrobiology and indeed astropaleontology. Cool question. Okay, I got another one. Miller just turned 9. Hi, Miller. And he wants to know, how do camera lenses pick up light? Good question. How do camera lenses pick up light? Well, in a camera, the lens isn't actually what picks up the light in the sense of detecting the light. What a lens is, like these lenses in my glasses here. Oh, they're dirty. That's disgusting. Sorry about that. Can we delete this part of the tape where you're seeing my... Actually, it's kind of cool though, right? To figure out where the camera is. Okay, like these lenses here, or the lenses in your eye. What lenses do, or in a telescope or in a camera, they shape the light coming in. They channel it, they bend it, they deflect it. So the lens is what focuses the light to the detector of the camera. And so the lens is not actually what's picking it up. It's the lens is what the light comes in and it sort of gets bent a little bit in the glass or whatever that lens is made out of. So they're not all lenses are made out of glass. When we sent a spacecraft to Venus one time, we had to make lenses out of diamond because glass would have melted. Weird, but true. But the lens shapes the light, channels it, focuses it, and then that light is going to hit something. It's like, let's go to the magic board here for a second. You remember this? This is my super high-tech... my super high-tech graphic interface here. Let's get a bright color here. if you've got, let's see, can you see this? Yeah. There's light coming from over here. Here's a lens of a camera or a telescope or something. And what it does, because of the shape of the glass, it will focus. The rays of light will bend a little bit on different parts of it so that it's focused in just the way that you want it. And then there's some kind of a detector here, and the detector is what picks up light. Now inside your eye, if this is your eye, then the detector is what you call your retina. This is the back of your eye. There's something amazing called a retina. And the retina is the part of your eye that responds to the light. Actually, what we talked about before, the photons, the particles of light coming in, and it sends little nerve signals back to your squishy little brain back there, and your squishy little brain puts an image together, and you go, oh, I can see. So the lens focuses it, the detector or the retina picks it up. Now in your camera, there's not a retina, but it used to be that there was film, and the light would expose the film, but now, of course, there's a... it's digital. There's an electronic device, which we call a CCD, a charge-coupled device. Don't worry about that. But basically, the photons come in and they knock out electrons. They do something funky to this detector, which sends a little, captures it in a little electronic signal, which then goes into a memory in your camera. So the lens is the focus, and then there's a detector that actually picks up the light. Don't you love my high-tech graphics? All right, let's see. Oh, and what does gravity look like? Man, Miller, you got the coolest questions. What does gravity look like? Well, I mean, we can't actually see gravity with our eyes, but we can see the effects of gravity. I mean, if you jump up and fall back to Earth, that's gravity. You're seeing gravity. And when we look at other planets, we see that the big planets are all round. The really little tiny lumpy things, which are, not even really planets, like asteroids or something in space. They're small, they're just like maybe 10 miles, 20 miles across. They look like potatoes. They're just lumpy little peanut things where, because the gravity's not strong enough to make them round. But if you make a planet big enough, it always becomes round because gravity will pull down the big mountains. And even Earth, you can see gravity. When you look from orbit, you see that it's round, and you see the mountains only go so high because of gravity. So we can't actually see gravity, but we can see the effects of gravity in so many ways. Now, there's another way though that we've learned to sort of see gravity, and this is pretty wild. There's something. It turns out, just like there are light waves we talked about last time of different frequencies, it turns out that in the universe there are gravity waves, or actually we call them gravitational waves. That there are particles, this is really weird physics stuff, but there are particles called gravitons that move through the universe and carry the force of gravity. And we've just learned recently to detect them. It's one of these things that physicists theorized. We thought, there should be gravity particles if we understand gravity correctly, but we've never detected them. Do we really understand gravity correctly? And this is what scientists do. They make predictions. They say, this is my theory of gravity. This is our theory of gravity. If it's correct, we should be able to detect these things called gravitons, even though nobody has. So then people worked for years and years and years and built these really complex machines that, according to the theory, should pick up these gravitational waves. And just recently, in the last few years, this experiment succeeded. So now we've learned to actually see gravity in a sense, at least detect it with instruments. So that's gravity looks like something. What does gravity look like? It looks like something very weird in space that we're just starting to learn how to see with our instruments. Let's see. Going back to Venus, there was a cool question I'm just seeing now in the stream that Nisha asked when I was talking about Venus. She said, is it very humid too? Is it very humid too because of the clouds? Great question, because we see the clouds and you think, oh, so it must be swampy and watery and wet. Scientists used to think that about Venus. When we observed the clouds with telescopes, we thought, oh, it must be all wet there because clouds are made out of water. And so it's a good question, Nisha. But it turns out that no, it's not humid on Venus. It's very, very dry, incredibly dry. And it turns out that those clouds on Venus that are everywhere and make it overcast everywhere and reflect so much light into space, they're not water clouds. We thought they were because we assumed, this is a mistake we make in science a lot, that you assume that if you understand something in one place that it's going to be the same in another place. So we thought we understood clouds. You know, I've looked at clouds from both sides now, right? We thought we understood clouds. And so when we saw clouds on Venus, we said, oh, we know about clouds, they're made out of water. But it turns out that when we go there with spacecraft and we measure them and we sample them and we drop probes through them and we look at in detail how they reflect light, they're not made out of water. And this is really weird, but the clouds of Venus are made out of sulfuric acid. Concentrated sulfuric acid. That's battery acid. Okay, that's like the stuff that is like really, really corrosive stuff. Like if you stuck your hand in sulfuric acid, don't try this at home, kids. You'd be like, ah, and you'd get burnt on your skin. It's like really intense stuff. So we not only are the clouds of Venus not water, but they're this really exotic chemical. It turns out called sulfuric acid. So that was sort of a surprise that we discovered. Oh, Hunter, age 15, wants to know what is in a black hole. Oh man, cool question. Hi Hunter. Hi Mary. How you guys doing? Okay, first of all, do you guys know what a black hole is? It's another one of these weird things that scientists predicted and you'd go, no, that can't be true. And then they went and did some observations and they found them and you went, wow, that really was true. And it's another thing that comes out of the work of, I mentioned Albert Einstein before, that brilliant German physicist. Well, he became an American citizen, but he was a German guy and a really brilliant, amazing man. And he came up with the theory of relativity. And I mentioned the special theory of relativity, which explains why clocks go slower, why time goes slower when you go near the speed of light. There's also something called, what is Gaia? Okay, Bonnie, we'll get to that. We'll put that one in the parking lot for a second. There's something called the general theory of relativity, which is another theory. And again, I can't go into the whole thing here, but one of the weird things about the universe that you learn from general relativity is that gravity isn't just a force that pulls things towards each other. We talked about gravity last time a little bit. It's not just a force that pulls things towards each other. It's also something that bends space. Like something really, really heavy, like a star, bends space a little bit. And if a star gets massive enough, you know, when stars form, there are clouds of dust out in the universe and gravity starts pulling in on itself and the clump pulls in and it gets more and more dense. And some stars, when they get massive enough, when they die, meaning when they've exhausted all their fuel and they can't shine anymore, they're so massive, they're so heavy that the gravity, their own gravity makes them keep collapsing, and they keep collapsing, and they keep collapsing, and they keep collapsing. And as they collapse, they get more and more dense, which means that there's more matter pushed into the same space. And as they get more dense, it makes them collapse even more. And they get, that collapse gets so strong, the force of gravity gets so strong that nothing can stop it. Not even the forces that hold matter, hold atoms apart, not even the forces there's no force in the universe that can stop that gravity when it gets that strong. And so it keeps collapsing and collapsing and bending the space around it so that it winks out. Poof, where did it go? Well, it basically makes something called a black hole, which has like, I don't know, it's weird, kids. It's weird, adults. It's just weird. It has infinite density. It's got all the mass of that huge star in a space that's basically no space. And it becomes something that is so dense that no light can escape it. Even light itself can't escape that force of gravity. And so you can't really see a black hole, but you can detect it because it has an effect on all the stuff around it. It's sucking in the gas and the other matter around it, and it's sucking it in so strong that it's ripping apart that matter, and that makes radiation. So it's disturbing the space around it, and you can see that disturbance even though you can't see the black hole. So, but the question that Hunter had was, what's in a black hole? What's inside? And the answer is really, really dense matter. In a sort of formless state. That's sort of an unsatisfying answer, but that's kind of the way we understand it. Now there's a possibility that because it collapses space-time, that some black holes might actually connect to other black holes elsewhere in the universe, and you might have something called a wormhole, which would be like a portal to another place in the universe. But we don't really know if that exists. There's some sort of science fictional ideas that might be true, but that, you know, physicists don't really know enough to say if they are true or not. So that, you know, so black holes are one of these weird things that we can describe. We've been able to detect because of the way they disturb the space around them. But to really understand what's in a black hole, you know, we have equations that describe it, but it's hard to really picture it because it would be so different from anything that we can experience and even relate to our own experience. It's hard to describe. Okay, so Bonnie had a question, what is Gaia? So Gaia is an idea about the Earth that is really kind of cool. The Earth is an amazing planet, as I'm sure you've noticed. And it's different from any other planet we know in the universe, even though we're looking for other planets that maybe have the qualities of Earth. We haven't found one yet. And the most amazing thing about Earth is that there's life here. And it's not just that, oh, there's organisms here and organisms there. There's a dog, there's a squirrel, there's a human, there's a bacterium, there's a plant. There's a redwood tree, there's a sloth, there's a paramecium, there's a mongoose, there's a koala. That's all cool. All the organisms on Earth are amazing, but combined, the total life on Earth, the sum of all the life on Earth and the way it interacts creates what we call the biosphere. And it's a part of the Earth that is really, as far as we know, unique. We're looking for biospheres, looking for biospheres elsewhere. But I'll give you an example of what I mean. Think of the gas that we're breathing. All that oxygen. Where does that come from? The oxygen comes from other living organisms. The trees and plants and plankton and algae, green growing things, are taking in other gases, carbon dioxide, water, and they're making oxygen. And then animals like you and me and your dog and that bird flying outside the window, animals are breathing that oxygen, and we're powering ourselves by reacting that oxygen with organic matter. We breathe it in, and we exhale carbon dioxide. And then that carbon dioxide goes back into the air, and trees use it, and they make oxygen. So there's a way in which the air itself is part of what we call the biosphere. There's parts of the Earth that are kind of alive, even though they're not parts of living organisms. It's all the life on Earth and the systems that interact with that life, the air, the water, even the rocks on Earth are transformed by life. And so we call that the biosphere, and some people call it Gaia. And Gaia is a name that means, Gaia is a goddess of the earth, and the Gaia Hypothesis is the idea that, in a way, the earth is alive. Now that might sound crazy to you when I say that, in a way, the earth is alive, because Earth is not an animal, it's a planet. It's rocks. It is, but it's rocks with all this life on it and changing it and being changed by it. And there are qualities, there are aspects, there are things about the earth that are like a living organism. For instance, why, if you look over billions of years of time in the history of the earth, the climate has stayed pretty constant. Okay, it's gone up a little bit, it's gone down a little bit, it's hot, it's cold, but it's never gotten so hot that all life dies out, and it's never gotten so cold that all life dies out. So the climate stays within a certain range. And the Gaia Hypothesis suggests that it's life itself acting on the planet that helps it stay in that range, and that other things about the planet are being regulated, are being controlled, are being we call it modulated by life. Just like inside your own body, there are processes keeping conditions within a certain range, like your temperature. If you get a fever, it's bad. If your body temperature gets too low, it's bad. But generally, your body stays at the right temperature. And we call that, it's a fancy word, but we call that homeostasis. It's the combined processes of all the things going on in your body, keeping the conditions in the way that life can continue in your body. And it turns out that the planet itself, Earth itself, the biosphere, has processes of homeostasis, that life is acting in some ways as to keep the conditions of the planet good for life. It's almost like Earth's biosphere is protecting itself by, we'll call it feeding back. I'm going to actually, the next Funky Science Story Hour is going to be all about feedback. It's going to be about a concept that relates to this, because feedback is cool. But I don't want to go into that now, because I'm going to do a demonstration next time. You know what? I'm going to play a song, and while I play that song, I'm going to play another song. If you guys come up with more questions, I'll watch them on the scroll. This is a song I actually just learned today, so it may not be perfect. It's like all science; it's a work in progress. But it's a fun one. It's a song I really like that I've always wanted to learn how to play, and I just learned it. And so it won't be perfect, but I'm gonna try to play it for you now. This is a song called. It's called "The Baby Tree." There's an island way out in the sea, where the babies, they all grow on trees. And it's jolly good fun to swing in the sun, but you gotta watch out if you sneeze. You gotta watch out if you sneeze. Gotta watch out if you sneeze. Yeah, you gotta watch out if you sneeze, for swinging up there in the breeze. You're liable to cough, you might very well fall off and tumble down, flop on your knees. Tumble down, flop on your knees. And when the stormy winds wail, and the breezes blow high in a gale, there's a curious dropping and flopping and flopping, and fat little babies just hail, hail. Fat little babies just hail. And in a pile, and the adults, they come after a while. And they always pass by all the babies that cry, and they take only babies that smile, smile. Take only babies that smile. Only triplets and twins if they'll smile. That's the baby tree. Okay, not a perfect rendition, but this is science, and we're always working on making it better, and that's what peer review, and that's the beta version of that song. Okay, now, I did get another question from Ilria Garcia, age 7. Hello, Ilria. Did I say that right? Illyria. What a cool name, Illyria. I hope I said that right. Wants to know, here's 2 good questions, both by Illyria. So the first one is about Jupiter's red spot. What is Jupiter's red spot? That's a great question. So you've probably seen pictures of Jupiter. Jupiter's the giant of the planets. It's the granddaddy of the planets. It's much bigger than any of the other planets in our solar system. And when you see a picture of Jupiter, you see these bands, these stripes, and these swirls of different colors. And everything you see on Jupiter is basically because of the weather on Jupiter and the storms and the winds. Because Jupiter's what we call a gas giant. It's this massive, massive ball of hydrogen gas and helium gas and other things mixed in, like methane and other gases that form the colors. And so when you see something like the red spot, it's a storm system, but it's a giant storm system. And it's a storm that's been raging for hundreds of years. The red spot is like a hurricane on Earth. You know, when you see pictures of Earth from space, you can see hurricanes, which are these swirling clouds, these storms, well, the air is swirling around and making a hurricane. And it's the same thing on Jupiter, but it's huge. It's 5 times the size of the Earth, one storm. That's how big it is, because the weather on Jupiter is so intense. And for some reason that scientists are still trying to figure out, this one storm, the Great Red Spot, it's the biggest storm on Jupiter. There are lots of smaller ones and they come and go, but the Great Red Spot has been stable. It's been sitting there swirling around for billions, not billions, for hundreds of years. We don't know if it's been billions of years because we haven't been here for billions of years, we humans. We've only been observing Jupiter with telescopes for 400 years, since the telescope was invented by Galileo 400 years ago. But in that time, the Great Red Spot has been stable for hundreds of years. And that's pretty amazing, and we're still trying to figure out why that is. And the red stuff is chemicals that are being formed by, there's methane, which is carbon, an organic molecule in the atmosphere of Jupiter, and it's being zapped by sunlight and forming more complex molecules, and it's these chemicals we call chromophores, which just is a fancy word for colorful chemicals that are made when the methane and some other things like phosphorus and nitrogen are in the atmosphere of Jupiter, and they're getting zapped by sunlight and forming more complex chemicals and then swirling around there in the atmosphere, and some of that stuff has that reddish color. Here's another good one, also from Illyria, age 7. Why do planets look like stars from the Earth? Yeah, because planets aren't at all like stars, but they do look like stars from the Earth. And it's because the planets are so far away. They're so far away that they look like pinpoints of light. Now, if you observe carefully, there are things you can notice about planets so that they're not exactly like stars as you see from the Earth. For one thing, when you look night after night, When you look, I'm almost done. When you look night after night, the planets are in a slightly different place every night. You can see Venus tonight at dusk. You should go out and look. It's beautiful. And if you look tomorrow night, Venus will look like it's basically in the same place. If you look the next night, it'll look like it's basically in the same place. But if you watch Venus for weeks, then you'll notice that it's going to start getting lower and lower in the evening sky. And then finally it's going to disappear from the evening sky, and it'll reappear in the morning sky because it's going to pass Earth in its orbit and be around on the morning side. And then months after that, Venus will disappear and it'll come back into the evening. And same thing with Mars and Jupiter. Night after night, they move around in different places because the planets are orbiting the sun just like the Earth is orbiting the sun. And so against the what we call the fixed stars, they're not really fixed, but they're really far away and we can't really see their motions very easily. So against the stars, the planets move around night after night, whereas the stars stay basically in the same place. And the stars come and go with the seasons, but they're the same from one night to the next. Now, another thing is that planets don't twinkle, and stars do twinkle. If you look at a star, especially when it's low in the sky, sort of not too far from the horizon, but still far enough so you can see it, you might see it twinkling. You know what I'm talking about. Stars kind of, they twinkle. They get a little bit brighter, they dark, they shift a little bit. And that's because stars, if you're in space, or if you're on the surface of the moon and you're an astronaut and you're looking at the stars, they don't twinkle. They look like they're twinkling on Earth because you're actually seeing the fact that you're looking through the ocean of atmosphere. You're looking through the air. And the air is moving around a little bit. There are breezes and currents and motions of the air. And it's because we talked about lenses before. Remember lenses bending light? Well, the atmosphere of Earth acts a little bit like a lens. And it's moving around, it's shifting, and you're seeing the twinkling of the stars is because of those little motions of the air, so that the path of the light coming into your eye from that star is shaking around a little bit. So why don't planets twinkle? Well, because planets are actually bigger than stars. They're not really bigger, but they're so much closer. It's what we call the apparent size is bigger. It's like, you want to know the difference between actual size and apparent size? Okay, right now, my head is actually bigger than my fist, right? When you see them at the same distance. But look what happens when I move my fist towards the camera. Now my fist is much bigger than my head. It's not really any bigger, right? But the apparent size is bigger because I moved it closer. Now the apparent size is smaller. So planets are much closer to us than stars. Much, 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 much closer. All the planets are orbiting around the sun. Maybe 100 million miles sounds like a big distance to you, but compared to the distance of the stars, the planets are all just like huddled around the sun. And because the planets are much closer, their apparent size is much bigger than the apparent size of the stars. And so you are seeing what we call an extended object. The star is just a point of light. And that point of light, you see it with the air movements, it's twinkling. But an extended source, it's not just one point of light, a planet, it's lots and lots of points next to each other. And so it's not going to, the image will be much more steady of a planet, and you won't have that motion because of the air that we call twinkling. So that's why stars aren't exactly like planets when we see them. Yes, we love it, we love it. Science! Cool. Okay, so we're going to do the Funky Science theme song now, and if you know it, or you know parts of it, sing along. And if you want to dance, I encourage that, because science is all, by the way, science is, music and science are very closely connected. We're going to do another whole lesson on music and science sometime in the future, but think about it. Why can you hear this? Because the string is shaking, it's vibrating, and it's causing the air molecules to vibrate, and the air molecules are vibrating and they're hitting the microphone in my gizmo here, and that's the microphone is turning those vibrations into electrical vibrations, which are traveling through the wire and then traveling through the Bluetooth and then traveling through the internet and then traveling up to a satellite and then to another satellite and then down to your gizmo and into the speaker in your gizmo. And that speaker is vibrating the air, and the air is going blah, 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 and it's going into your ears, and it's shaking little hairs on the inside of your ears, which turn those vibrations into nerve cells, which go into your brain. And so all that happens, and you go, oh, he's playing an A. And why is this an A? And this is also an A, but it's a higher A. It's a much higher frequency. That's because I'm changing the length of the vibrating string, and so the wavelength of the waves, just like we talked about wavelengths of light, the low frequency, the red light, is these long wavelengths. Well, the high frequency is much shorter wavelength, sound waves moving through the air. We're going to talk about sound and vibration on a different lesson, but just so you know, music and science, it's all related. Everything is vibrations and waves and rhythms. The motions of the planet are rhythms. So we're gonna talk about all that if you stick with me on future Funky Science Story Hours. But I've used up plenty of your time. So we're going to go out on the Funky Science Story Hour theme song, and then we'll take up more of your great questions and more fun funky science next time. All right? So now work on your dances for this, okay? Everybody dance. Gather around, my children. Pull up a chair, my friends. Let's all get together for the story that never ends. How did we get here? What's inside your head? What's bluer than blue? What's redder than red? Gather around, my people, all children, young and old. Pull up a seat. Put up your feet for the greatest story ever told. Funky Science Story Hour, 'cause not... Let's try that again. Funky Science Story Hour, 'cause science is knowledge and knowledge is power. Because the world is so and weirdness is fun, and there's so much to learn, and we've all just begun. I'm gonna do that again because we can do it better. 1, 2, sing it with me. Funky Science Story Hour, 'cause science is knowledge and knowledge is power. Because the world is so weird, and weirdness is fun, and there's so much to learn, and we've all just begun. We can understand the weather. We can imagine ourselves in any place and see the earth from outer space. How? With science. Funky, funky science. Science, science. Funky, funky science. Oh, funky, funky. Funky science, yeah. Everybody, with science. Funky, funky science. Oh, science, science, science. Funky, funky science. Oh, funky, funky, funky science, yeah. All right, funky boys and girls and men and women and everybody else in between and otherwise. I love you all. Live long and prosper. And I'll catch you next week for the episode 3 of Funky Science Story Hour.